Hello, you guys. It's Mrs. D. I just want to take you on a really quick tour of the periodic table, just to help you out a little bit and as a quick review. So let's get started. Let's take a look first at our lovely alkali metals. Now, the alkali metals here, you'll see that I'm outlining in red. The alkali metals are very reactive in water. The reason is they have one valence electron. One valence electron. The reason why they just have one valence electron, with that, it's very easy for other elements to take that valence electron. So that's why they're so reactive, especially with water. They can actually just kind of explode upon water. That's why we do not find these in nature. We find them in compounds, and then we often refine them if we need to. Also notice too, hydrogen is not considered part of the alkali metals. Hydrogen's kind of its own thing, its own family, so just keep that in mind. The second thing on the periodic table is we have the alkaline earth metals. The alkaline earth metals are very much like the alkali metals, but they have two valence electrons instead. We have two valence electrons, and those two valence electrons are also easy to access. So that means that other elements can go after them. And remember, like I told you, it's not like a kind donation. It's not like, oh, here, take my electrons. It's like other elements saying, give me all your electrons. Going on to the next section, we have in the middle, we have the lovely transition metals in this middle section here. Oh gosh, that was a bad line. Okay, so it does go right along through here. So the transition metals in this section here, those transition metals, sometimes it's hard to predict the valence electrons for transition metals. It depends on a lot of things, depends on the situation, depends on what they're bonded with, depends on the temperature sometimes, or it depends on the amount of energy. So basically, though, when we think of valence electrons, we think of those outer shell electrons. Well, actually, with valence electrons for the transition metals, sometimes we can grab some of those electrons that are sort of in an inner type of shell. If we keep moving on, we're going to go over to the halogens. Oh, I didn't mean to do that. Halogens are here in this section. The halogens are a little bit different because they have 7 valence electrons. So just a quick reminder here, with valence electrons, we can look at our representative elements and get the valence electrons. So if we come up here, we have 1 valence electron in this column, 2. We're going to skip these because they're not dependable just looking at the periodic table. 3 valence electrons, 4, 5, 6, 7, and 8. And we will find that that magic number of 8 as we get into electron configuration is really, really helpful. And you'll kind of put it all together after we do electron configuration. But just know at this time there's 7 valence electrons, but that also means these are very reactive because they only want 1 electron. Since these elements here, atoms of these elements only want 1 electron, they bond easily and readily because they're going to go after those with just 1 or 2 electrons to bond with. Finally, if we go back here and we get to the noble gases. So we have our good old noble gases in this last column or last family of the periodic table. The noble gases have 8 valence electrons, so they do have a full outer shell. Noble gases typically do not bond. Notice I say typically, 9 times out of 10 they won't bond, but there's always that chance. I hate to say never in chemistry because never is a very strong word in chemistry. We look here though, and a lot of people ask me, well, what are all these sections here? Well, we'll find in just a second, a lot of these are metalloids, and we'll also see that sometimes we just refer to this as the oxygen family, the nitrogen family, the carbon family, and the boron family, just to place ourselves on the periodic table. The last section I want to point out on the periodic table is the inner transition metals. It's this whole section down here. And these inner transition metals, what you have to realize is where they take place on the periodic table. So you'll see atomic number 58 right here, and it actually goes up here to atomic number 57. And you'll see 90, and it goes right in here. So we're kind of like squeezing those in right here. And if we actually put them in on the periodic table, this periodic table would be so long, we'd have to get 2 pieces of paper at least to show our periodic table. So ultimately, we don't use these as much. Many of these, after what we call transuranium, meaning after uranium, many of these are made because of radioactivity from other elements. They're not found in nature. Let's take a look at metals, metalloids, and nonmetals here, just to show you the dividing lines. So let's take a nice thick red line here to show you the metalloid line. It goes under boron and starts a stair step. And these metalloids are very much like, they can do both. They can behave like metals or nonmetals. Now keep in mind though, that metals are on this side of the periodic table and nonmetals are on this side. And the stair step is what divides them. Now, we also know that there's some definite characteristics of nonmetals versus metals. We also realize that nonmetals typically make anions, meaning that they are electron takers, where metals typically make cations, which means they're electron givers. The only metalloid on the periodic table that actually is a metal, even though aluminum is on the periodic table right next to all the metalloids, this is actually a metal. So please, that is one exception on the little stair step. The rest of them, boron, silicon shares one, germanium, arsenic, antimony, tellurium, polonium, and astatine, sometimes they act like this and sometimes not. But I want you to see though, these are, again, semiconductors. They're great for our phones because they can allow the voltage to go through and they can stop it. So we won't lose our batteries in the drop of a hat. Anyway, that's just the basics on the periodic table. We love this thing. And remember, of course, who told the elements where to go? And we have good old Dmitry Mendeleev. So he is the one given credit for the periodic table. And we're talking, this is about the time period of the 1860s. And the 1860s was a major chemistry time period. It was after we've discovered protons, neutrons, and electrons, but before we've really started to look at even the Bohr model at this point. So keep that in mind, keep that in the time frame, and if you have questions, make sure you ask. Take care, guys.